Hello. Let's take a look at how we can derive the fundamental pricing partial differential equation here. Now, in order to achieve that, let's first take a look at what we need to have, and then we'll take a look at what we need to do to derive that pricing PDE. Now, first of all, we need to have an underlying asset, and we need to know what stochastic process that underlying asset is following. So you can say that I have a stock as an underlying asset, then the stock follows a log normal process. Now you can also have another asset that follows a different process, not necessarily a log normal process, but nonetheless you need to have an asset that follows some sort of a stochastic process. Then you need to have a derivative asset. Uh, the price of the derivative asset is then a function of the underlying, the price of the underlying asset. And this function needs to be a differentiable function of the price of the underlying asset, and also a differentiable function of time. And in this case, if you know the stochastic process of the underlying asset, then by Ito's lemma, you will then know the stochastic process follows by the price of the derivative asset. And you will see that both the underlying asset and the derivative asset will have the same source of random factors. So essentially, in the random process, the randomness or the random changes are caused by the same random innovations in both of the stochastic processes. Now, what do we try to achieve once we have those things? Well, our ultimate goal is really to have a functional form. This functional form that links the price of the underlying asset and a bunch of other parameters you know to the price of the derivative asset. So what are the other parameters? Those things are like interest rate, volatility, things like that. So once you have a functional form, you can then derive the price of the derivative asset, okay? And in addition to that, you can take partial derivatives on that functional form. Let's say if you have a closed formed solution, you just simply go there and take partial derivatives against several parameters, against the price of the underlying variable, the underlying asset, the interest rate, volatility, and a whole bunch of other things you can think of. So the sensitivity is actually very important. That tells you, if something were to change, how would the price of the derivative asset will respond to those changes. Now, how we're gonna do that? So here, we're gonna first of all talk about the basic ideas behind them. Then we'll look at the math to see how the actual formula or the actual form of the PDE will be derived. Now the ideas are, well, first of all, once you have the random process that you specified for the underlying asset, and you also have through Ito's lemma, the random process for the price of the derivative asset. Then there's one thing you can do. You can then try to form a risk-free portfolio. By a critical step for forming that risk-free portfolio is to have to determine this delta. So in our last lecture, we see that we actually derive what that delta was by looking at the condition where no matter whether it's an up move or down move, that portfolio has to have the same value. So essentially, the risk-free portfolio constraint determines the delta unit there. Now here, we're actually is doing almost exactly the same thing here. So first of all, we say that delta is equal to the partial derivative of the price of the derivative against the price of the underlying asset. Now, this may not seem like the same thing as we talked about last time in the last lecture, but very quickly, when we actually try to derive that, you will see that by having this is a necessary condition to form a risk-free portfolio in continuous time. Now, once you have this condition here, you can then follow what we have talked about last time, have delta units of the underlying asset, long delta units on underlying asset, and short 1 unit of the derivative asset. And then you will see that that particular portfolio is actually risk-free, i.e., the current value of the portfolio and the future value of the portfolio are totally deterministic. And being a risk-free portfolio, that means this portfolio must grow at the risk-free rate. Okay, so the difference between the future value of the risk-free portfolio and the current value of the risk-free portfolio is really this growth of the risk-free rate. Then you have this condition here that enables you to obtain a fundamental differential equation. Okay, so once you obtain the fundamental partial differential equation, you can solve that. You solve that if you are lucky, you can solve it with a closed form solution. So that means there's a pricing formula explicitly. Now, if you're not that lucky meaning, depending on what kind of stochastic process you assumed for the underlying asset, some of them will lead to a closed form solution, but if you assume something very complicated, then you may not be able to have a closed form solution for the partial differential equation. In that case, you can always then resort to a numerical method to solve for the price of the derivative asset. Now, if you have a closed form solution, you can just directly take partial derivatives to get your sensitivity. And if you do not have a closed form solution, then you can numerically taking partial derivatives numerically, then you will also be able to conduct sensitivity analysis.